Going live now, yes sirree. Okay, elemental analysis. So this is a little bit more mathy math work where we can see how we get those percent compositions. Again, just adding more stuff onto the beginning. So, you all want to talk about propane? Propane accessories? So, here we have propane and oxygen make CO2 and H2O. All the propane is burned and it produces carbon dioxide and water. So a little bit of whatchamacallit, stoichiometry. 1 gram of propane is 0.02268 moles of propane, which, when you burn it, will produce, with an excess of oxygen, will produce 0.06803 moles of CO2 and 0.09071 moles of water, or a little less than 3 grams of CO2, a little bit more than 1.6 grams of water. This is how we find our mass percentages. We burn some amount of our unknown, and we collect the oxide products that it produces, so carbon dioxide and water in this case. So we burn 1 gram of some substance, some unknown substance. This produces 3.380 grams of CO2 and 0.6919 grams of water. First, we convert back to moles for CO2 and H2O. But then we also have to convert to moles of the element. Okay, we're not particularly interested in the oxygen, not really, okay, because the oxygen came from here, the stuff that allows it to burn, not here, the stuff that makes it, the substance. So we go to moles of the compound to get to moles of our element. Okay. So every molecule of CO2 has 1 atom of carbon. Every molecule of water has 2 atoms of hydrogen. So basically, the moles of CO2 will be equivalent to the moles of carbon, but the moles of water will only be half as much as the moles of hydrogen. But then we also have to do a thing. We have to check our composition, because oxygen sort of disappears in these things. Okay. Oops. Let's bring up the page. Let me show you. C3H7O H. Yeah, whatever. So this is propanol, rubbing alcohol, plus oxygen yields CO2 and H2O. So even though there's oxygen in our original compound, we don't really see it as a separate thing over here. Okay? So that's why I'm saying we need, let's see, is it going to be, so 8, 12 plus 8 is 29. There we go. All right. So you burn propane, which is very similar to this, except it doesn't have the oxygen in it. You're going to get CO2 and H2O. You burn propanol, which does have oxygen in it. You're also going to get CO2 and H2O. So we don't see it as a separate product, which is why I include that extra step. We have to convert back to mass to check composition. We'll see over the many examples that I work through that very often, when you convert back to mass, your carbon plus your hydrogen will add up to the original mass you started with. But if it doesn't, that means that somewhere in here, you have oxygen hiding. So you have to look for it, you have to find it. So that's why I include that step. Most things, everything else will combine with oxygen to make a separate oxide, but oxygen won't do that, because it's already there. So it's going to be sort of hidden, sort of buried. So if there's oxygen in your compound, you have to look for it hiding to see if there's anything missing. All right, so let's go ahead and work through this. Burning 1 gram of a thing produces CO2 and H2O. So 3.380 grams of CO2 times 1 mole of CO2 for every, molar mass of carbon dioxide is 44.009. Calculator. 12.011 plus 15.999, and there's 2 oxygens. Wow, okay. So 3.380 divided by 44.009 means we have 0.07680 moles of CO2. But like I said, we don't really care about the CO2 so much as we care about the carbon. So now we convert to moles of carbon, but there's 1 mole of carbon for every 1 mole of CO2 because nice 1-to-1 ratio. So 0.07680 moles of carbon. And we do the same thing for water. How much water? 0.6919 grams of water. 18.015 grams per mole. 0.6919 divided by 18.015, 0.03841 moles of H2O. But then we have to double that because there are 2 moles of hydrogen for every 1 mole of water. Okay. So that's going to get at 0.07682 moles of hydrogen. So be careful about that. Okay? Going from these raw numbers to mass percentages. Well, you're not really going to mass percentages. You're going to the empirical formula kind of directly. Mass percentages are kind of universal in general. These would be the actual raw numbers. But now, like I said, to be cautious, you should go ahead and convert these back to grams so that you can double check that there's no hidden oxygen. So 0.07680 times 12.011 means we have 0.9224 grams of carbon. 0.07682 times 1.0079 means we have 0.0743 grams of hydrogen. Let's add those together and see if there's any missing mass. Okay. So 0.9224, 0.07743, 38999. Okay. So barring rounding errors, this adds up to a total of 1 gram, which, if you look at the original problem, that's the amount of the substance we originally started with. So there's no missing matter. Okay. If the number was, significantly different, then that would mean that some oxygen had been hiding somewhere. Okay. So we would have to include and account for the oxygen. But because there's no matter missing, there's no oxygen in this compound, so all we have in this compound is carbon and hydrogen. And you can see, again, barring rounding errors, 7680, 7682, we have the same amount of each. The empirical formula for this compound is just CH. Okay. So that is how you get from these raw numbers to an empirical formula. And if they give you the molar mass, then you could then find the molecular formula in the exact same way. So step 1, you convert your masses to moles. Then you got to remember to convert to the elements. So there's 1 atom of carbon in every molecule of CO2, so it's going to be the same number, but you have to double it for hydrogen because there's 2 atoms of hydrogen in a molecule of water. And then, just to be safe, you have to double check, make sure there's no missing mass. So you convert them back to mass, add them together. If there is missing mass, then you have oxygen hiding somewhere in your compound. If there's no missing mass, there's no oxygen. And then you go back and you check your mole ratio. Okay. If you do have hidden oxygen, you have to take that mass, convert it to moles, and then also include it in this last step. All right, let's look at another example. Why do we not? So we have 1 gram of something produces carbon dioxide and water. 2.273 grams of CO2, 0.9305 grams of water. Let's go ahead and find the empirical formula of this here mystery compound. 2.2703 grams of CO2, divide by the molar mass of CO2. 0.05159 moles of CO2 is just the same thing as 0.05159 moles of carbon. And then, because we're going to be double checking, times 12.011, 0.6196 grams of carbon. And then we do the same thing with water. 0.9305 grams of water divided by the molar mass of water. Oops. 9305 divided by 18.015. 0.05165 moles of water, which we have to double because there are 2 atoms of hydrogen in every molecule of water. So 0.1332 moles of hydrogen. I could have just done that. Wow. 1033. Okay, I screwed that up horribly. That's why you don't do math in your head, people. Then we multiply that by 1.0079 to get the mass of hydrogen. We have 0.1041 grams of hydrogen. Now let's go ahead and check for missing oxygen. 0.6196 grams of carbon, 0.1041 grams of hydrogen, adds up to 7327 grams. We started with 1 gram, which means we are missing some material. We have hidden oxygen in this particular compound. So how much oxygen do we have? Well, that's 1 minus 0.7237 3672 grams of oxygen. So now we have to also find the moles of oxygen, so we divide by the 15.998 grams per mole. 2763 divided by 15.998 is 0.01727 moles of oxygen. So now we have our 3 moles: 1727, 5159, 1032. All right, so let's go ahead and write those down side by side to make this slightly easier. 0.1033 moles of hydrogen, 0.05159 moles of carbon, and 0.01727 moles of oxygen. So clearly the smallest number is this one, the 0.01727. So to find the ratio, we divide all of them by this guy. And that is going to get us a number, C3H6 Okay. So that is the empirical formula of this compound. Again, we can't find the molecular formula without the molar mass. But once we have that, we could then go on to do the exact same thing we've done before. So now here's another example. Go ahead, pause the video real quick, and see if you can't work this out on your own. Don't forget to check for hidden oxygen. I'll wait. Okay, welcome back. Let's go ahead and work through this bad boy. Okay. What you chirping for, Sasha? You want to play with your big brother Wesley, but he is not in a playful mood at the moment? Oops, I can't use my calculator if I don't have my calculator up. So 1.373 divided by 44.009. And then it's a 1-to-1 ratio, so 0.03120 moles of carbon. And then, being cautious, that is also 0.2729 grams of carbon. And now we do the same thing for the water. 1.124 grams of water divided by 18.015 grams per mole. And then it's a 2-to-1 ratio, hydrogen to water. Never forget that. If you forget it, you'll get wrong answers, and then your parents won't love you anymore. They will be deeply, deeply ashamed of you. Giving us 0.1248 moles of hydrogen. And again, being cautious, times 1.0079 is 0.1258 grams of hydrogen. And oh yeah, there's definitely matter missing. So 0.2729, 0.1258, 7893. We are missing an awful lot of matter. So the 1 gram we originally started with minus 0.39873106 means we have 601 grams of oxygen. Divide by the 15.999 grams per mole. Convert that back to grams. 0.601 divided by 15.999 means we have 0.0376 moles of oxygen. Did I screw up somewhere? That seems weird. Let me double check my numbers. 1.373 divided by 44.009. Also 2.011. Yeah, I definitely screwed up. I screwed up horribly. Because it's not 2729 grams of carbon. It's... Okay, so these numbers are all going to be different. Okay, so it's not 2729, it's 0.3747. How the heck did I do that, I wonder? Let's see, where's the 2747? Or 2729. Oh, I divided 12.011 by 44.0. Why the heck did I? That's weird. I really got that monstrously wrong. And none of you were around to stop me. I blame you, honestly. You should have been double checking me. Now let's double check the water. One, 2, 4, 8. Okay, now we multiply that by 1.0079. Okay, good. That number was correct. So 0.3247 grams of carbon and 0.1258 grams of hydrogen. Okay, we still got missing matter. 5054. Okay, so 1 gram minus that is 0.5405 grams of oxygen. We convert that back to moles. That's going to give us see, that's why it's important to check. I'm screwing up my math all over the place. 0.03435 moles of oxygen. That still seems weird. What is our moles of CO2? That's still 3120, and it's still 1248 for the water, for the hydrogen. I'll roll with it. Because when we look, we now see that this is the smallest one. And it's not going to make a good ratio with oxygen. 1373, 1124. 1.373 divided by 44.009 times 12.011. I keep on... Okay, in this case, it's because I couldn't read my handwriting. It's 37, not 32. 5005. Oops, that number is correct. This one was not. Because now 1 minus 0.5, oops, 0.3747 plus 0.1258, 1 minus 0.5005, 4995, divided by 15.999. Okay, 3120. All right. So the reason I was saying that these numbers were off is because it wasn't producing a nice ratio. And it wasn't producing a weird, an understandable ratio. It was going to be like, 5/7 or something. It was going to be incredibly, incredibly weird. You expect it to be a whole number multiple, like 3120 and 3120. They're the same. The ratio was 1 to 1. Or it could be 3120 to 6240, a 1 to 2 thing. Or 3120 to 1248, a 1 to 4 thing. Okay. So you divide all of these by 0.03120, and you're going to get CH4O. So the fact that it kept on coming up with these weird numbers that were close but not quite right, that's why I was thinking that there was a mistake there. It's because it should be either almost exactly the same or a whole number multiple, not something that's just a little bit off. Because when we look at it, 425 divided by 0.0312, that would be 1.098, right? That's a little too far off for me to really be comfortable calling that the whole number ratio of 1. It's just weird. Okay, and it doesn't look like a regular sort of oddity. because you don't always get a 1 to 2 or a 1 to 3 or a 1 to 4 ratio. It's possible to get other ratios. And this is as good a time as any to discuss that, because like, what if you were looking at S2O3, right? That's a perfectly feasible sort of compound. If you were to, burn this, collect the product, what you would get would not have a 1 to anything ratio. Instead, it would be a 2 to 3 ratio. It would be like 1 to 1.33. No, that's 1 to 1.5. There we go. So that would tell you that you have not a 1 to something ratio, but a 2 to something ratio. You have to multiply both of these by 2. It's way too far from a whole number. You can't really round this. You just multiply both of them by 2, and that would tell you that it was S2O3. You could also get 0.25 or 0.33 or 0.66, 0.75, and 0.5 right there in the middle. So this would tell you have to multiply all your numbers by 4, multiply them all by 3, multiply by 2, multiply by 3, multiply by 4, right? It's possible to get those fractions. If you're way far away from a whole number, either you've done something wrong or you just don't have a 1 as your smallest number. You have a 3 or a 4 or something like that. So again, this is all perfectly 2, 3, or 4, all perfectly reasonable, perfectly valid ways that this could work. But that 1.09, that was not it was too close to be a reasonable fraction like this, but too far for it to be correct. So I mean, they're almost certainly not going to give you a 5 to 7 kind of ratio. They'll probably give you something much. In fact, I would be kind of surprised if they gave you something like this. It wouldn't be out of line, but you're mostly going to have empirical formula where the smallest number is 1, and thus you would have nothing but whole numbers. This would be perfectly reasonable, but even that would be a little bit strange. But no numbers beyond that, I would not expect that. So if you're seeing really wild fractions, double check your math like I just had to do. So, all right, we are out of examples. That was nice and instructive, I think, that long string of mistakes I made. But that is it for this evening. Coupled with the lab videos, I did 4 videos tonight. So I'm going to go ahead and save the remaining 4 videos of Chapter 6 for tomorrow night. And then on Sunday evening, I will start Chapter 7. And with that, I will go ahead and bid you adieu. See you around.